Welcome to the TransferLab seminar, which is part of the Applied AI Institute for Europe. Our seminar is a platform where researchers and engineers share and discuss recent advances in AI and machine learning. In today's seminar, we have Pulkit Tandon, who will talk about a statistical theory of data selection under weak supervision. Pulkit is a research engineer at Granica, where he focuses on data selection, compression, and optimization for AI applications. He also serves as an adjunct lecturer at Stanford University, teaching courses on data compression. He holds a PhD in electrical engineering from Stanford, with prior experience in Netflix working on video encoding. His expertise lies in statistical learning, machine learning, and optimization in both academia and industry. Thanks a lot for being here, Pulkit, and now the stage is yours.
Thanks, Jan, for the introduction. Thank you for the invitation for me to talk about the work. Happy to be here. Today, I'm going to be presenting to you a work towards statistical theory of data selection under weak supervision. And this is a joint work with German and Andrea. It's almost no surprise to anyone that modern AI is really hungry for data. And the bigger your model is, the more data they consume. So, okay, this is a cartoon image from ChatGPT. But this is really true. So if you are an empirical machine learning engineer or someone in academia, I'm pretty sure you have heard of scaling laws at this point. If you are a company who's trying to train a machine learning model, the conventional wisdom which has come out these days is you would like to probably scale on one of these 3 parameters and you would immediately get some sort of improvement. Here, I'm pulling up a plot from Kaplan et al. From 2020, where the y-axis is test loss and the x-axis can be compute. So scaling compute, you can decrease the test loss. Or if you make your models bigger and bigger, so scaling the parameters, again decreases your test loss. Again, another slightly underrepresented topic is you also scale your dataset sizes quite significantly. And that also results in a lower test loss, right? So what have people been doing? They have been collecting more and more data. They have been training bigger and bigger models. And they have been training it longer to eventually lead to some of the fancy gains which we see all around us. But if you think about it, more data actually has some costs associated with it, some real costs, right? So as you increase data, your labeling and storage costs increase. So now you have to store this data. You have to somehow go acquire those high quality labels for this data. Not only that, your training time increases actually quite significantly, which makes like empirical machine learning engineer in the industry, that would mean like you now will have much slower iterations on whatever you are working on. Not only that, this makes the whole thing again more computationally expensive, like it costs you more. And finally, as your data increases, it's really hard to account for data quality. These days, you just go scrap the web. But if you think about it, like all the premium models, a lot of these data points are really low quality. They are basically extremely low signal, high noise. So it becomes harder and harder to get those quality data points in a way to train your models. So this is really the punchline. Like, okay, sure, we want more and more data. However, if you think about it, not each data point is contributing equally. So here's an example. So on the left, I'm showing you a GIF, which is collected from images collected from an autonomous vehicle. This is from Kitty 360 dataset. And what you see here is just the front camera view of this car going collecting images. And this is the video which you get. Now, let's say you are an AV autonomous vehicle engineer, a perception engineer. One of the tasks which you might want to do is train some neural network model to maybe detect cars on the road. So in this particular scenario, you are going and acquiring all these images with the eventual goal of detecting the car. Now, if we take a minute and think about it, not all images in this scenario would be contributing equally to the end goal of detecting a car. So when you put that data point in the machine learning model, not each data point gives you equal boost in terms of how better you are becoming in detecting the car. For instance, in this particular case, you see there are like a lot of images which are basically just contiguous blocks and provide little to no information. Like just adding all of these data points, after a while, there would be a diminishing return. On the other hand, there are other classes of images which might be very helpful. So there are some images which have these cars, like really parked in various different situations, or maybe scenarios like this, where it is even more critical to detect that there is car, even when there is much fewer car points. So what this is really highlighting is that even though when we train our machine learning models, most of the time we treat each data point going into our pipeline as something which is equivalent in the contribution, that's not really true. And this phenomena actually is not new. This has been seen in a lot of different empirical results in various different settings with various different complexities. So all of these different works saw something similar. However, most of these works really looked at it from an empirical angle, and it was unclear what is really contributing to this phenomena, in the sense that like they were training complicated neural network models, they were working with complicated tasks. Even though this phenomena was clearly evident in their numerical results, it was hard to pinpoint and understand what's really causing it, so on and so forth. So I guess in this work, basically what we ended up doing is showing that something like this is actually quite omnipresent and even true in much, much simpler settings. The thing which I want to highlight is, so now here, what I'm showing is a misclassification rate versus data sampling plot for the case when you are training a logistic regression model for the previous task which I shown. So again, you have these bunch of images, you want to detect a car. Let's not do anything complicated. Let's just train a logistic regression model on top of it. I'll be showing you a bunch of these plots. So let's really understand these plots clearly. So on the x-axis here, I have the percentage of data subsample. So as you move towards the left, you are basically using fewer and fewer training examples when you are training your machine learning model. On the y-axis, we have the misclassification rate. So this is the test error on unseen samples. And here, as you go up, you have higher test error. So ideally, we want to be somewhere on the bottom left or below in all of these curves. A curve which will be shown below is typically better because it will have a misclassification rate which is lower at maybe looking at similar data, or it is getting the same error looking at lesser data. And the green line here, which I'm showing, is the full sample error, which is what's the misclassification rate if, in this case, you were taking the whole data set and training a logistic regression model on top of it. Now, the black line which you see here is the performance you get for this task when you randomly sample a subset of the data. So this point is saying that, okay, I'm going to go randomly sample 40% of the data. What's my misclassification error? It's approximately 8.75, which is in this case higher than the full sample error, which is what you would conventionally expect. However, what we show in this work is that quote unquote smart sampling can actually beat random significantly. Lower curves are better. The blue curve here is the smart sampling. And what you see is that, again, it either achieves a much lower misclassification rate for similar amount of data, or you can see that it has similar misclassification error even after throwing away significant data. And I'm being ambiguous about smart for the moment, but we'll clarify what exactly smart means. So again, this is really surprising. I want to highlight this fact. So in this case, what you really see is that you can get full performance after throwing away 65% of the data set. So you're getting the exact same misclassification test error, unseen samples, even after throwing away a significant chunk of the data set. And again, these numbers, these specific numbers are true for the experimental settings you worked in, and they would change, but still highlights the phenomena which we are seeing here. And even more surprisingly, what you see here is that you can get better performance than the full sample estimation with only 60% of the data. So reading it out loud, what this point is really saying, you can throw away data and even get improvement in your test error. And again, as a reminder, this is not for any complicated task. This is not for a large neural net with hundreds of bells and whistles. This is a vanilla age-old logistic regression being trained on this images for a classification task, really a setup which a lot of people understand. The goal of this work was we saw these surprising effects and we wanted to understand them better. So far, I have talked about toy cases, but I haven't really described formal setup in which we are really studying it. So before we go into the formal setup, this is really an informal setup of experimentation and how we are thinking of data selection in this particular scenario. So in our case, we start with some unlabeled data. So you can think of each of these squares as some data points. And then we use a data scoring network to assign some score to each data point. So you can think of these as some sort of data importance score. So in this particular diagram, the darker the colors, the bluer the colors, the more important those data points are. After you have scored this, you can rank your data set and do some sort of data selection. So far, we have not used the actual labels anywhere in this pipeline. So you have a data set which is completely unlabeled. But at this point, you go and acquire labels for just this subset, and then you use this data set for training. So this is really the setup under which we will be studying data selection. Before we move on, I want to highlight a few different parts of this setup, which are really important. So the first one, we have a two-step procedure in the sense that we first have a selection step, which is done over unlabeled data set, followed by training, which is done only over the selected subset. This is interesting because like many times we are collecting data sets out in the wild, but it's hard to actually get good quality labels for this data set. For instance, like the autonomous vehicle example, which I showed there, that's like a real use case. If you are in California or Bay Area, you would see many of these autonomous vehicles just roaming around and collecting a bunch of images. They have to go store these images, and then somewhere it is decided which data points to go actually collect labels for, because labeling is much more expensive process than just acquisition. So this setup allows you to work in a setting like what I just described, where you start with an unlabeled data set and maybe you go and acquire labels only for some small subset, which can be very useful in practice. The second highlight here is that we are working in a weekly supervised setting. So the paper titles and the talk title says weak supervision, but what does weak supervision really means? What it means is that even though we start with access to data set with no labels, we do assume we have access to some quote unquote surrogate model. What do I mean by a surrogate model? So you can think about it basically as us knowing something more about the labels than just random guessing. You can think of it in today's world as maybe a foundational model, which is trained on some task, or maybe previous iteration of your last model, or maybe another model which was trained on a different data set, and now you want to train a model on some other data set. What the surrogate model is really doing is, okay, you are not starting from zero, you're not starting from a random guess, but it's giving you some information about what these labels could be for each data point. The next aspect is that we do a score-based subselection. Okay, so what this data scoring network essentially is being used for is, after some massaging, you sort of use the information on this data scoring network and your data to essentially get some important scores. What these important scores really are is, one way to probably think about it is, let's say you have a classification task. Then you can think maybe how easy or hard was an example to classify for this data scoring network. That's an idea of score. So you had a foundational model, or maybe you had a model trained on another data set, and now you want to come and look at your actual data set. What this scoring network is doing is, maybe you are looking at each data point and seeing how easy or hard was this point for the surrogate model to classify. And finally, the last aspect of a setup, which is important, is that once you have these scores, it's not always that you pick the highest scoring points. You may want to pick the highest scoring points, or you may want to sample these points with some other probabilities. What this means is that we sort of have a probabilistic scheme where you're not enforcing the target size strictly, but rather in expectation. And this seems again trivial point, but we'll show some in some results that this is actually extremely important for your schemes to work. So that was an informal introduction. So formally, we study weighted empirical risk minimization. This is like the standard empirical risk minimization setup, where you have n data points over which you have some loss function depending on labels and whatever model you are building, and some general regularizer, right? So this is textbook weighted empirical risk minimization. The only place where this subselection is being introduced is this term SI. All I want you to take away from this part of the slide, that formally any subselection scheme in our setup can be defined by a tuple, which is this pi I wi. What is this tuple? So pi I is probability for point I. In our scheme, we independently decide to select a point in the subset with probability pi I. So this is not a group thing. This is like for each point, maybe you go toss a coin, you decide with probability pi I to keep it in the selected set. And then once this point is in the selected set, you actually weight the empirical risk minimization term by W. So you assign some weight to it. Okay, so this is really a quite general subselection scheme in itself. You may decide to keep each data point within your empirical risk minimization or not, And if you decide to keep it, you might want to upweight it or downweight it. To the next part, which is in this case, a tuple, which is again indexed by I. So this tuple is for each data point. It can be different. In our case, it can depend on your features xi because you have the data points available. It can depend on the surrogate model, which is some conditional probability distribution given these features xi. So this is like another foundational model trained on some other data set, so on and so forth. And finally, we have a probabilistic scheme, like I was just describing. So like these tuples can depend on additional independent randomness. Something to highlight, this tuple does not depend on the labels yi because you have no knowledge of what these labels are when you're doing the selection. So we take this setup in our paper and then we actually quite rigorously analyze it under various different settings. And I think all of this is really important. I won't be showing a lot of mathematical proofs today, but I'm happy to talk about these setups formally at the end of the talk. But it is really important to sort of highlight these differences because I think we spend quite some time in understanding how each of these affect subsampling process. So the first axis really is the bias versus unbiased sampling. What do I mean by that? An unbiased loss function post-sampling assumes that your weights are going to be inversely proportional to the selection probability, right? So if you want to keep this loss unbiased, if you input a point with probability pi, you need to weight that point by 1 by pi. So that's an unbiased scheme. Unbiased scheme essentially becomes like your weights are not really independent of the selection probability, whereas in biased schemes, your weights can be anything, essentially. Why this is important? It's because a lot of work in the literature really focuses on unbiased sampling. So if any of you have heard previously about leverage scores in linear regression setting, or maybe influence scores in logistic regression setting, all of these techniques essentially are unbiased sampling techniques. But one might question, why do we want to stick with just unbiasedness? And in fact, this is going to be one of the punchline of the results that you don't have to. You can actually get a lot of gains if you move away from just doing unbiased sampling. Next, we also study our setup. Our work is a mixture of theoretical and empirical findings. So a lot of theory in the paper. But another setup which we try to delineate in our work is we study asymptotics under both like high dimension versus low dimension. What I really mean by that is, again, if you go look at the literature, a lot of work really do sampling where they assume that the number of points which they are sampling are much lower than the actual set which you start with. So where that is interesting, on the other hand, that doesn't really go highlight the practical scenario where most of the times you don't want to throw away most of your data points. You would rather have something where your subset size is comparable to the original data set size. The eventual goal of doing this data selection is to keep as close as possible or even improve the test error efficiency. It's not really to throw away most of the points and just for fun seeing which one data point is really important, right? So this is exactly what we do. And we try to also add another axis to it, which is whether your models are basically under-parameterized or over-parameterized. And we see some interesting finding there. So what I mean by the high, like more concretely, like the high dimensional asymptotics, we study this proportional high dimensional asymptotics where your subset size, small n, your actual data size, capital N, and the number of parameters in your model all go to infinity. However, you assume that the subsampling fraction tends to some constant gamma. And then in the high dimensional proportional asymptotics, you assume that your number of parameters are also scaling proportionally to the number of data points. So this is like a very standard setup, if you know about it. If not, it's very interesting because in this setup, you can really understand a lot of mysterious effects which showed up a few years, maybe 5 years back, things like double descent and so on and so forth. And yeah, so this provides an interesting control in our experiments. And again, I'm not saying this just for fun because what we see is also very interesting aspect that when you have data points, which you might want to select very different data points, depending on whether you are in a low dimensional regime or if you're in a high dimensional sort of setup. And we'll see that in results. And finally, in our paper, we also study imperfect versus perfect surrogates. What I mean by that is the surrogate model is a really important part of our data selection scheme, right? In the case of perfect surrogate, you assume that you know the true conditional distribution. Whereas in the case of imperfect surrogates, you might not know the true data distribution, true conditional data distribution. Even though like imperfect is more realistic, obviously you never know the true data distribution of this conditional. Even then, what we see is that in the case of perfect surrogates, we still see a lot of different interesting results because this problem is still constrained and non-trivial. And then again, in the results, I'll show you some surprising aspects of how this affects the selection scheme. So like I said, we are gonna study two main schemes. So one setup really here is, like I said, like one special case is this unbiased loss function setup, post-sampling, which is where your weights are inversely proportional to the selection probability. Another very interesting setup, which we study specifically for the bias case, is what we call non-reweighted subsampling. And the idea there is that weights are just one. So what that allows you to do is, in that case, you can just do the selection. You can think, oh, I'm just going to select a point with probability pi I, and then I don't change my procedure at all. So that's an interesting setup because that allows you to do selection while not really changing any of the downstream training pipeline. So in that case, like let's say whatever training empirical risk minimization setup you have already working for you, all you decide to do is whether you keep a data point in or not with probability pi I. And then you don't change any weights or anything. So that's like one example of bias sampling, which is really interesting, of practical interest, and which we actually study in detail in the paper. So I have described you the setup formally for like various different theoretical settings we studied in the paper. But for the remainder of this talk, actually, I'm gonna focus on something very simple, which is the binary logistic regression. So we are gonna just look at cases where your labels are binary, and we are gonna just look at a model which is logistic regression. And our sub-selection scheme is going to be something which looks like this. So where you have p times 1 minus p raised to alpha. Looks complicated, but let me break this down for you. So basically what this is, probability SU is probability under surrogate model. So again, you have some data point I, you apply the surrogate model, and this is the inference probability which you get. Then this p times 1 minus p is something which you can think of it as an hardness score, or as a question was asked earlier, this is like a measure of the uncertainty under this surrogate model. Why do I call it hardness score? It's because, so here's just a simple plot of this quadratic function. So if you think about it, when your surrogate model is really confident about its prediction, when your surrogate model is like, so the probability of inference for the surrogate model says, hey, this is definitely not a car, or hey, this is definitely a car. In that case, your p times 1 minus p is going to be 0. Other ways to think about these points is that these are like easy examples under surrogate model. Your surrogate model is very sure about these examples. On the other hand, you might have some examples where your surrogate model is completely unclear on what's the inference probability. And in that case, like your p times 1 minus p will be really high. So if your, for example, p is 0.5, that's when this function is maximum. So at that point, your surrogate model doesn't know at all, hey, I'm completely unclear given this image if there was a car in it or not. And so it's really a hard example under the surrogate model. So this thing, you can think of it as hardness score. And then we also have a parameter alpha, which essentially determines the hardness. So when alpha is greater than 0, you upsample the hard points, whereas when alpha is less than 0, you would upsample the easy points in your selection scheme. So we take the subselection scheme and we do experiments in two different setups. So we have a setup of synthetic data, in which case we actually study isotropic Gaussian covariates. So basically your features xi don't give you any information about the selection in the asymptotic setting. And then we assume that the true data model is a generalized linear model, which can either be well or misspecified. What I mean by that is like, so, okay, first of all, my probability y equals to 1, given xi is going to be some linear function of the features. So that's like the generalized linear model. And then what I mean by well or misspecified is whether this distribution, this function f, is actually logistic regression or not. It's actually logistic function or not. Because it's possible you might want to use a cross entropy loss or a logistic regression, even though the true data distribution is not actually logistic. So this kind of highlights that. And then on the real data side, I'm going to show you more results with like this car detection task, which I showed you before. I've talked a lot about different setups and settings. So now let me get into some of the concrete results. So like I said, we have a lot of theory as well as numerical results. And the main point which I want to highlight here is that in our case, theory ends up predicting the exact high dimensional asymptotic test errors. So what I'm showing here in all these 9 plots is each of these plots. So this is a 3 by 3 subgrid. Each of these plots is the same thing which I showed you in the beginning of the talk, where y-axis is the misclassification rate, x-axis is the subsampling fraction, and you want to be on the lower Pareto front. The lower, the better. The different colors which you see here, we are just focusing on one of the plots. The different colors which you see here are basically different hardness coefficients. So the warmer colors is when your alpha is positive and you decide to upsample hard points in your subsets. Whereas the cooler colors is when your alpha is negative and you're upsampling the easy points in your subset. So you have the scoring mechanism and you may decide to upsample either the easy points or the hard points in your subset. So different colors are showing that. Black is again random. So these plots are for the synthetic data, and the different subplots which you see they are under different signal to noise ratio for generating this data or for different regularization. Something I should have highlighted earlier is that we are working on a ridge regularized logistic regression. So that's really the model. Too much information here. Don't worry about all these 9 plots. That's not what I want you guys to do, keep looking on all these 9 plots and figuring out the patterns. All I want you to highlight is in these plots is that the circles, all the dots which you see are via simulations, whereas all the solid lines you see are actually not interpolations of these dots, but rather the theoretical predictions of what the empirical risk minimization would be in this case. So even though it feels like the lines are actually interpolating the points, if you look closely, they are not. These are actually the prediction. So what I really want you to take away is like, okay, a theory is quite accurate in a variety of different settings. As shown in this plot, it can capture a lot of non-trivial behavior, which you see also in the experimental setup. And I've described to you, if you think about it, a really simple setup, right? Like the previous slide wasn't complicated at all. It's just vanilla regularized linear regression trained on a binary classification task. In a synthetic data case, it's like probably the simplest data model you can think of. And even this simple setup surprisingly demonstrates many interesting phenomena. So next, I'm going to summarize some of the findings from this work, right? Like in this setup. So the first finding really is that the unbiased subsampling can be suboptimal. So in this case, we are now using real data AV data set. Again, the same plots, you're going to be seeing a lot of them. But in this case, like the different colors which you see are whether your subsampling scheme chosen was unbiased or biased. Like we discussed earlier in the talk, the unbiased schemes kind of generalize a lot of different popular techniques, right? Influence function-based sampling in case of classification, or leverage scores in case of linear regression. And that's here the red curve, which is this unbiased sampling. Whereas the blue curve, which you see here, is the case if you do biased sampling. And in particular, since we have already discussed, this is with non-reweighted sampling. So you're not doing anything special with the weights. You are just keeping the weight 1 and you're deciding whether to keep a data point in the subset or not. And what you see here is that the biased sampling is lower, right, than the unbiased sampling. So even though the unbiased subsampling could beat the random, so this is already some sort of smart subselection, the bias can beat the unbiased one much more. In our paper, we show that under certain natural settings, we have multiple theorems as well as specific constructions showing that your unbiased sampling can be arbitrary worse. So what really it does is like it opens a line of inquiry that maybe we should look more into biased sampling and not just the unbiased sampling techniques. The next thing is like, if I were to ask you at the beginning of this talk and given you nothing, and I would have said, hey, tell me how would you do subselection if you had another model? This is probably what you would have said. Like I would use that model and maybe I'll go pick up the hard points. I would go pick up the data points, which I'm really struggling at, and I would put it in the subset for my next model to really go train. And this is exactly what we see. So in this setup, we see that choosing hard is better than not choosing random data points. So what I'm showing here now is the different colors here represent different values of alpha. The warmer colors is when your alpha is positive. The warmer the color, the more positive it is. And you're upsampling the hard points more in your subsets. Whereas the cooler colors here are when your alphas are negative and essentially you are upsampling the easy points more. And what you see here is two things. One, what you see is that choosing hard examples work. Again, all of this is very specific to this. Like I'm cherry picking some examples to drill, to give some take home points, but we can dig deeper into various different situations. The point here really is like choosing hard examples really work. However, this dark blue curve, if you see, that's what we call hard top K, like with these triangles going down, which is when you don't sample. but rather you pick the top k hardest points. And if you see in this scenario, like your picking hardest examples can lead to catastrophic failures. Like this red curve, just even though all the red ones are almost coinciding till this point, after that, your darkest red curve, the top k curve, just blows out of proportion. So this is where I'm going to tie back to the earlier point that doing this probabilistic sampling of keeping a point in or not is really important. And if you just go pick up the hardest point, it might lead to some very bad results. The story is actually much more complicated. Actually, in high dimensional settings, choosing easy is better. So this is where we bring back why did we study low dimensional asymptotics versus high dimensional asymptotics. What we see is that in general, when you have over parameterized models, actually choosing hard examples is bad. You may want to choose easy examples, and this may sound counterintuitive. So again, this is like a similar plot where each of the subplot is basically misclassification rate versus a percentage. Different colors are different levels of hardness, whether you're upsampling easy or hard. And again, I don't want you to look at all of these curves, but what I want you to focus on is the bluer curves. So the curves which upsample easy examples are consistently below in this setup across all these different SNRs and regularization. And this is very surprising if you think about it. But this is also something which has been seen in some of the previous results, which, like, for example, there's this paper by Schorcher et al., which saw the same setting for margin-based classifiers. What we did in this work is generalize this and actually show and see that this might be much more common in general if you have a high dimensional setting, which is an over-parameterized model, which is where a lot of today's practical models are, right? Like you have much more parameters in the model than the actual data points. Another way to think about, for example, as you go from left to right, in this case, you see blue curves being down to red curves being down. So this is like another example, like how much you regularize. You may want to pick hard examples or easy examples. And one way to think about it intuitively, like if you forget all the plots, if we were just discussing at a coffee shop and I ask you, hey, when do you think always giving me hard examples to the model is the best? You would probably come back and say, maybe no. If the task is really hard, I don't want to bombard my model with really hard examples. I would rather have my model take some easy examples and learn the general structure of the problem before I actually go ask it to learn all the fine nuances, right? And so in that setup, it's very easy to think about it intuitively, but maybe in the over-parameterized setup, it's even more, it just shows up more generally. So the next point which I have is, surprises, is that actually one might think a better surrogate model always leads to better selection, right? Like, oh, if I had a model which is perfectly trained on my data set for my task, maybe I can exploit it better for this classification of easy or hard. What we see is that that's not always true. So now in this plot, the different colors which you see, we vary the strength of the surrogate model. And the darker color basically means like you have a stronger surrogate model versus lighter color, you have a weaker surrogate model. And in this case, what I mean by a weaker surrogate model is that it was a surrogate model trained on some independent data points, which are actually much smaller than the original training data set. So in this case, weaker surrogate model was just trained on 4% of the data points. And then it was used to create these selection probabilities and to do selection. And what you see here is that this light red curve is much below compared to like when you would train a stronger model where you would use maybe another independent data set, which is almost half the size of your original data set. And this is very surprising that weak supervision, again, that the surrogate models trained on far fewer independent samples, is actually sufficient for effective data selection. And also encouraging. That means that you don't actually have to go out in the wild and come up with the most accurate surrogate model to be able to do some smart sampling. Rather, it's okay if you don't come up with the most accurate surrogate model, because more accurate surrogate model can even hurt the data selection performance. This is like really surprising result. And I think last point, which I want to make, but definitely not the least, is that I started this presentation by showing you this sort of magic effect where subsampling was able to beat full sample training. A lot of other people, like I described, have seen the same thing under different complicated setups when they train large neural networks on complex data sets, complex tasks. But what I show here is that we can see this even for this simple task for synthetic data. So if you look at this plot, again, different colors are whether you're upsampling easy or hard examples. But if you see this data point, what you see is you were able to throw away almost 60% of the data and improve on the misclassification test error. So this is not, so again, this is a cherry-picked example, but this is something which can arise naturally under certain settings in our setup. And what I want to highlight that even though this is confusing, this does make sense. So we observe this in the case of misspecified models. So essentially the case when true data does not follow logistic distribution. If you think about it, you are training when you train a loss function, there are inherent assumptions. So things like, oh, my actual data distribution is logistic. That's why you are fitting a logistic probability distribution on top of it. But what this shows is that, hey, if your actual data distribution is not logistic, but if you have a mismatch between your loss function and the true data distribution, then each data point might not actually provide equal value to you. In fact, it can even hurt the performance. It can be of extremely low SNR. So I think this is really the one-line intuition of why you might see such effects. So just to conclude, I think in our work, we had some surprises. So things like popular techniques using unbiased sampling can be actually extremely suboptimal, or use of weaker surrogate models can outperform stronger surrogate models. However, I would say the main insight coming out of work is it corroborates a lot of previous different studies where it says that the uncertainty-based subsampling can be effective, though like choosing hardest examples can be catastrophic. And depending on various different settings, maybe choosing easy examples can be more beneficial than hard examples. And I'll encourage you guys to go read the paper for more details. This is like a meme which I really like. If you follow XKCD, came out long time back, where it argues that, it basically argues about the data. And what I'll suggest is that in this particular case, don't stir the pile of the data set which you have, rather be selective about what you feed your machine learning models. Thank you for inviting me.